The occupancy probability is another key quantity, and what this describes is the chance that an electron is actually going to be in a particular available electron state. Now, once again, there is an equation which you don't need to know or use, although what I will point out is that in this equation there is energy minus the Fermi energy. That's what the probability actually depends on. So the probability is dependent essentially on how far the energy that the electron has is from the Fermi energy. Now, what's really important for you to know is the shape of these graphs. Now, this top graph here is actually a graph at 0 Kelvin, so absolute zero. And what you'll notice is the electrons have a 100% probability of being in those states up until, so the states have a 100% probability of being filled, I should say, up till the Fermi energy. And at this point, it drops down to a 0% probability. And it hopefully makes sense to you from our coverage of the Fermi level why this takes place. So the Fermi level is essentially at absolute zero. How high will the filling of electrons go? So every single state up to that Fermi energy level will be filled. And that's because all the electrons at absolute zero will have the minimum amount of energy they can. So they'll drop down to the lowest possible energy states and fill every one of those states they can. Now at a higher temperature, at a temperature above 0 Kelvin, we get a shape more like this. You'll see now there's some probability of electrons having an energy greater than the Fermi level, and the probability just below the Fermi level has dropped. And this is because some of those electrons have been promoted by thermal energy to high energy levels, and they've started to spill beyond the Fermi level and fill those higher states. So there's now a probability, some finite probability of electrons being there. So that's really the key to what you need to know here, is just be able to identify those graphs and understand why the probability looks the way it does.